In this video, we are going to discuss bandpass filter. What is bandpass filter and how to design it using RLC circuit. That we'll be discussing in detail. So this is one bandpass filter. It's a system. It can take one input signal VIT and it will produce corresponding output signal V0T. So for bandpass filter, what will happen? It will allow to pass a band of frequency of input signal through this system and it will be available at the output end. Input signal can have many frequencies, low frequency, mid frequency and high frequencies. Only mid frequencies will be allowed to pass and very low frequency will be rejected, very high frequency is also rejected. Okay, in this way bandpass filter will work. So how to characterize this one? So what we can do, we can go for this Laplace domain, the input Bi S and this output V0 S. Its transfer function is given by H of S, which is nothing but the gain V0 S upon VIS. Okay, so for AC signal we have seen that H of S, their S is replaced by j omega. This will give you the magnitude or gain for AC signal that we have discussed in detail in my previous videos, low pass filter and high pass filter. So if you have not gone through, please go through that one first, then you can come back here to watch this video. Here we will be discussing the bandpass filter with respect to low pass and high pass filter. So this gain H of j omega, its magnitude will give you this magnitude m of omega. Okay, that plot is important. Ideally, for ideal filters, bandpass filter, what are the characteristics? This is omega. If I plot this magnitude plot, I have said that a band of frequencies, suppose this is one band, it's omega C1, it's omega sub C2. Within this one, these frequencies are allowed to pass. That means the gain, can have the gain 1 within these frequencies. Just 1 minute. So this is the gain 1. So in this region, the gain is always 1. So that's how it is called pass band. I'll call it, it's a pass band. And you can see that when omega is more than omega C2, then that signal cannot go through, it's a stop band. Again, this side, when omega is less than omega C1 up to 0, it is also stop band. Right? So a band of frequencies within this omega C1 to omega C2, that signal can pass through the system and it will be available at the output end. Right? Now, in practice, what kind of response you will be getting? So this is one ideal. This is called ideal bandpass filter. So what you can get in practice, so that response will be a little bit different. You cannot get this kind of sharp cutoff frequencies. So this is omega and this one is m of omega. So instead of this sharp cutoff, so it will be gradual one. So you may get this kind of response. Okay, so you can get maximum magnitude somewhere here, and that frequency could be considered as center frequency, WC. Then this side, so if its magnitude is A, so at this point where you will be getting A upon square root 2, and here also we can get another frequency. This frequency I'll call WC1 and this is WC2. So these two are 3 dB cutoff frequency. This and this one. This is lower 3 dB cutoff frequency. This is upper 3 dB cutoff frequency. But remember that the maximum gain here at omega c is A, and here you should get A upon square root 2. So in dB scale, already I have discussed in detail in my previous videos. It is corresponding to 0 dB, and at this magnitude you will be getting it is minus 3 dB. Thus the gap is 3 dB. That's how these frequencies are called 3 dB cutoff frequency, or it is called also half power cutoff frequency, because whatever power it will be there here P0, at this frequency you will be getting P0 by 2, or here also you will be getting P0 by 2. This is half power cutoff frequencies. Okay, so this is in practice. In practical, bandpass filter characteristics could be like this. Now how to design bandpass filter using low pass and high pass filter, because we know what is low pass filter and what is high pass filter. Okay, so we want to implement this bandpass filter in terms of low pass and high pass filter. So one easy way is that to consider. So this bandpass filter we can get if we cascade one low pass filter and one high pass filter. So low pass filter followed by high pass filter can give you one filter. So this is combined one. I can say this will behave as bandpass filter. Okay, so how it will work? So this is your input signal, right? BIT, this is output signal B0T. So this filter, suppose it is H1S, this is your H2S. So as it is a low pass filter, we can draw the low pass filter characteristics, right? So this is your frequency omega, and its cutoff frequency I am considering WC2, and its cutoff frequency I am considering WC1, right? Now try to understand what is this. Now can you draw this low pass filter characteristics? Its magnitude will be 1, so I will take the different color. So it will be 1 up to omega c2. So its magnitude ideal. I am going for ideal one. So this is for low pass filter. I am plotting this magnitude plot. M of omega. Okay. This low pass filter means magnitude of H1 of j omega. Okay, I hope you can understand this thing. This is basically magnitude of H1 j omega, its magnitude. Correct? Now second one, high pass filter. How can I draw the high pass filters? So high frequency will pass through, so that I can consider here. Suppose this is your WC1. So beyond WC1, so 0 to omega c1, it is absolutely 0, and beyond that it will be 1. So these characteristics is your high pass filter, and that we have drawn for mod of H2 of j omega, right? So now we can see that if we cascade these two, so already we have seen this thing, that this is for low pass filters, this blue one, and this one is for high pass filters, and output of this one, total filter characteristics, if we can combine this H filter is H of S, is the product of these two, H1S and H2S. So when one filter is 0, so for very low frequency, high pass filter is 0. 0 is multiplied with 1, it will become 0. And right side again, if I multiply, this is 1, high pass filter is 1, but low pass filter is 0, the product of these two will be again 0. So resulting things you can see that it will be 0 here, again it will be 0 here, right? So in between omega C1 to omega C2, both are 1 1, so their product will be 1 into 1 is 1. Okay, so overall characteristics will be like this. So this one will be for band pass filter. If you cascade low pass and high pass, then you will be getting band pass filters. But remember one thing, that cutoff frequency of low pass filter, this omega C2, it should be more than omega C1. This is the requirement. The cutoff frequency of low pass filter should be higher than cutoff frequency of high pass filter. And if it is not so, then what you will get? Okay, you can think of this one. If WC2 is less than WC1, what you will get? Okay, let me know your answer in the comment section. Okay, so right now you can also see these things, that here what kind of frequencies we are getting. For low pass filter, we will be getting from 0 to omega C2. Those frequencies only available at this stage. And out of this, omega C1 to up to infinity, those things only it will be available. Okay, so omega C1 to 0, from here whatever frequencies there 0 to omega C1, those will be rejected and rest will be available here. That means only omega C1 to omega C2, these frequencies will be available at the output end. So first low pass filter will remove the high frequency components, then high pass filter will remove the low frequency component below omega C1. You will be getting a band of frequency between omega C1 to omega C2. An important thing is that this order does not matter. First you can consider low pass followed by high pass, or high pass followed by low pass, you will be getting the same thing. Only thing is that you need to check that cutoff frequency of the low pass filter should be higher than cutoff frequency of high pass filter. If you don't do these things, you won't get band pass filter. That time what you will get, you can write in comment section. Okay, next. So how to then, once you know these things, easily we can design the band pass filter. Okay, so can you recall what is the low pass filters and high pass filters using RC filters? We can easily design these things. Okay, so in the first two videos we have designed low pass and high pass filter. In low pass filter we will get this kind of structures. This is R, it is C, right? So this filter will behave as a low pass filters. This is your input, and if you take output from capacitor, it is a low pass filters. Okay, that I have already discussed, because for low frequency capacitor will behave as open circuit. This is simply open circuit. Okay, in that case this total voltage will be available here. But for very high frequency signal, capacitor will behave as short circuit. So its potential will become 0, output is 0. That means high frequency signal cannot go through. And for this one, we have got the H of S as well. So what is the H of S? I said that this capacitor should be replaced by 1 upon Cs. Then we have obtained the H of S, that is your transfer function, V naught S upon VIS. What is this? 1 upon Cs. This is the impedance. And by total 1, R plus 1 upon Cs. So it will be 1 over 1 plus RCS. That we can write 1 over 1 plus S over omega C. So here omega C is the cutoff frequency, and omega C is simply 1 upon RC, which is 1 over time constant, and that is unit is radian per second. So that thing we have discussed in detail. So in low pass filter, we will be taking output across the capacitors. We can also design low pass filter using inductors. How we can design using inductors? Very simple. That time inductor should be here and resistance should be here. This is inductance L, this is resistance R. Okay, this is your Vi and this is your V naught. So you will be getting, again, this is also a low pass filter, because very low frequency inductor will behave as short circuit. If it is short circuit, full voltage will appear across these things. But very high frequency inductor behave as open circuit, so output is 0. Okay, and transfer function you can also find out quickly. This is R, the inductor reactance is Ls, R over R plus Ls, and that you can simplify it. This is 1 over 1 plus again S upon omega C, where omega C will be how much? Again 1 over time constant, and in this case time constant will be L over R. Okay, that means it is R over L, that is in radian per second. So that thing we have also discussed. So this is for low pass filter, and similarly for high pass filter we can get. So if so far you are enjoying this video, can you please press the like button? Thank you. Now we can get corresponding high pass filters. How will get high pass filter? For high pass filter, capacitor should be here and resistance should be here. We should take output from resistance and input is connected here. This is the capacitor C, the resistance R. Okay, what the transfer function H of S will be very similar, 1 over 1 plus, this time here it is S and here it is omega C. Or this thing I can write in opposite way. This is S over S plus omega C. Okay, and where omega C is same thing, 1 over time constant means 1 over RC. Okay, we can also design this. This is your high pass filters. Same high pass filter we can design using inductor. In that case, this is the resistance and this is the inductor R and inductance L, and this is Vi and it is your V naught. For this one HS, again it will take the same shape, 1 over 1 plus omega C by S, or we can write S over S plus omega C, where omega C is 1 over time constant, and this time time constant will be 1 over L by R. Okay, that is radian per second. It is also a high pass filter. Right? Now, to design a band pass filter, what we can do? We can cascade these two together, one low pass and one high pass. We will be getting a band pass filter. So how to get a band pass filter? So can I consider this thing? So this is band pass filter we can get. So for band pass filter, if we can design like this, okay, what is this? This block. So this block is a low pass filter. Can you identify? Because we are taking output across the capacitor. Okay, next I need one more block, and that would be your high pass filter, and that we can use using capacitor as well. This is a capacitor, and then followed by resistance. This is your input and this is corresponding output. This is R1, R2, C1, C2, and you can see that here this block is behaving as high pass filter. Just thus the total one, this total low pass and high pass combination, I can write it is a band pass filter. So in band pass filter, H of S could be like this. I can write S time 1 plus S upon omega C1, 1 plus S upon omega C2. Okay, so we'll be getting 2 poles and 1 0 at the origin. That is the form or transfer function of a bandpass filters. So here you can see that it is product of this one 1 upon 1 plus S upon omega C1 multiplied by S upon 1 plus S over omega C2, or it is omega. Okay. So this will behave as a low pass filter and this is a high pass filter. But remember that just cascading these two, it is not the same as omega C1, omega C2 is not only R1 C1 and R2 C2, not like that. You can't get like this because there is a loading effect in between these two stages. If we include one buffer in between, then we can multiply it safely. Otherwise, you can't do. Okay. So if my circuit is like this, suppose if this one and this one, these two, if I cascade through one buffer circuit, okay, and how can I design buffer circuit? I can use one op amp. This is a negative terminal, it is a positive terminal, and negative one I can just connect here, then go for this. So this will give you a buffer circuit, voltage follower or buffer circuit. Okay, this is your R1 C1, this is C2 R2. In this case, it is fine, absolutely fine. So its time constant will be R1 C1, its time constant R2 C2, and you will be getting of this form, right? But not for this one. So it is more complicated. Okay, you need to find out the overall things. But you will be getting a second order equation in denominator and one S you will be getting in numerator. So this kind of poles and zeros we will be discussing in one video later, not here, right? So many ways we can design bandpass filters. You should check it, right? So one more example. Suppose if I consider this is one inductor and this one is resistance. So what is this? This is a low pass filter. Okay. So I need to consider one high pass filters followed by. What are the high pass filters? So if I can consider this thing, again one capacitor and one resistance. So you can check this one, this block, this inductance L and resistance R1, the capacitance C, it is R2. So this is your low pass filter because you are taking output across resistance for RL circuit. And this one is your high pass filter. So one block is low pass, other one is high pass. So total one is band pass filter. Another example you can check. Okay. So if I go for in this way, this is capacitor, this is the resistance. Okay. And then if I put this is the inductor and this is one resistance. Right. Will it give again bandpass filters? Because first one, your high pass filter, and second stage is low pass filter, no problem at all the order. Again you will be getting band pass filter. Right? So any two, one low pass, one high pass, this combination will give you a band pass filter. No way you can design band reject filter in this way. Okay, so that will be discussed later on. Now using RLC circuit also we can design band pass filters. So how can I design the band pass filter? Can you check these things? So if I consider one inductor, one capacitor, and here is one resistance. Okay, this is inductance L, capacitance C, and resistance R. This one is your VI, This is your V naught. So what is the transfer function? Can you find out? Okay. So this one. So how to get transfer function? I have said that inductor should be replaced by Ls and capacitor should be replaced by 1 over Cs. Then try to use potential divider circuit. So Hs is nothing but this one, B naught S upon Bis is the gain, and that is potential divider here. It is R. Across resistance we are taking output. So this R self resistance by total impedance. This is R plus this resistance is Ls, and this one impedance is 1 over Cs. So if you simplify it, what you will get? So Cs will come over here, it will become RCS, then you multiply these things, it is RCS plus LCS square and then 1. Okay, so you can see that H of S is taking this form. So RCS over LC square RCS plus 1. So this will provide you 2 poles on the left hand side of S plane, and this is 1 0 at origin at S equals to 0. So whenever you will be getting 1 0 at the origin, 2 poles on left side, it will behave as bandpass filter, but that thing will be discussed in detail in another video. But again, it is giving you bandpass filter. Can you check with input DC signal and high frequency signal? How can you check that it is really behaving as a bandpass filters? And that is very easy. So how can you check this one? Already I have mentioned this thing, that this circuit, this one inductor, first inductor, then capacitor, and this is the resistance. So this circuit we want to understand, inductance L, capacitance C, it is R, this is your input, this is output. Now can you check with the DC input? If I apply DC signal, I said that for DC, what is this? Inductor. Inductor is behaving as short circuit, and capacitor will behave as open circuit. That thing we have discussed several times. And for AC, high frequency AC, inductor will behave as open circuit and capacitor will behave as short circuit. Okay, that thing only can do. So what we will do? For DC, this is your inductor, this is capacitor, then this is resistance. Just you can see. So for DC, inductor is shorted. Okay, I can make it shorted. But capacitor is open. This is open. This is short. This is for inductance. This is for capacitance. Okay, and this is your resistance. So if input is Vi, what is the corresponding output? You can see that as this part is open, no current will flow. It is 0 ampere. So if 0 ampere is flowing, so there is no voltage drop across resistance, so output voltage is 0. Means DC is blocked. DC cannot be available, cannot be available at the output end, cannot pass through the system. Now can you try with high frequency AC? Okay, so high frequency AC, that we will try to analyze. Again we will consider this is your R, this is your Vi. We want to understand what is the output, and this time for high frequency AC, inductor is open circuit. So this is open, it is kept open for inductance, but for capacitance, what we will do? We will make it shorted. Okay, it is shorted, but effect is same because it is open. No current is going through here. That means again no current will be available here. 0 ampere. So output is again 0. So very low frequency cannot pass through. very high frequency. This is a very high frequency. High frequency AC signal cannot also pass through. So only mid frequency, they will offer certain impedance here, some impedance here, and you will be getting certain output here. Okay. So you will be getting some output for mid-band signal. Very low frequency signal cannot pass through. Very high frequency signal also cannot pass through. So it will behave as band pass filter. I hope you have understood these things. Okay. So we will be discussing more about this pole geolocation and everything others for bandpass filters. So keep watching, and if you enjoyed this video, you can just press the like button, and if you have not subscribed the channel, you can subscribe it. I will be discussing more problems and more ideas in this channel. Keep watching. Thank you.